the volumes of revolution. First, we'll focus on the method of discs or washers. Let me introduce the whole thing with a simple example. Let's start with the graph of y equals 1/3 x. I don't want a good graph of this. I just want a rough sketch here so you get the idea of what we're going to be doing. Let me graph it. Roughly. I know it goes through 0, 0. And then when x is, say, 3, y would equal 1. So we have a pretty thin disk, a 1/3 slope line. Now, what we're going to do with this particular graph is we're going to take it, or at least the graph of the line, and rotate it about the x-axis. So revolve, I think that's the word more books use, revolve the line y equals 1/3 x about the x-axis. So I'm going to drop, for the time being, I'm going to drop a lot of the numbers because they're not important. I'm just going to focus more on the pictures and what happens. So let me graph this again. I may go a little more grievous with the slope, but there's 3. Now, if I rotate that around the x-axis, so that's this guy here, imagine it revolving around and around and around. And imagine it going infinitely fast. You can see a shape occur. If it's revolved around there, you'll see a shape like this occur. You get a cone. In fact, with this cone, if you look at it, the height of the edge of the cone was 1. Of course, 1 through 0, 0. Now, let me just take this cone here. Let me just take any old cone. If you know the radius and you know the height, let's call that the height, the volume is given by V equals 1/3 pi r squared times h. Instead of memorizing the formula, which it should be something that everybody knows, but instead of memorizing the formula, you'll notice that it is 1/3 pi, but pi r squared is the area of this circle that's the base, and then the height. A lot of figures have formulas for the volume, something like the area of the base times the height times something, or just the area of the base times the height. It depends on the shape. So it's an easy way to remember such things as this. So for our particular example here, the volume of this thing here would be 1/3 pi. R is 1, and then h is 3. And this equals pi. Keep that in mind, because I want to redo this example, but use calculus methods, or the methods that we use in calculus to derive these volumes. I'll show you how it works. Let's Let's use calculus to do this. All right. Let's go back. The equation was y equals 1/3 x. And the graph looks something like this. So it went to a height of 1 when x was equal to 3. All right, what we're going to do is, for the time being, I'm going to deal with the area underneath of this curve in such a way as to use the old, do you remember the old Riemann Sums we did at the end of last semester? And you might do right-hand endpoints. If you remember this, etc. You probably remember the very first one here. That was x sub 0. Then you had x sub 1, dot, dot, dot. Probably somewhere around here you had x sub k, dot, dot, dot. And at the very end you had x sub n. That was the last endpoint. Well, instead of just trying to take the volume like we did before, what we're going to do is work with these things. If you look at these things, they're rectangles. And if you remember, according to the Riemann sums, we would add up the areas of these rectangles to approximate the area under the curve. Then we would let the number of rectangles increase to infinity, which would force the thicknesses of all the rectangles to go to nothing. Therefore, the area in the rectangles would eventually become exactly the area under the curve. And taking a limit, we usually had some formulas to work those out. We can kind of work that a little bit here. Let's take a look at if we rotate this instead of the actual graph. So if we rotate this around the x-axis, what are you going to get? Well, you're going to get something that looks like this. You're going to have, at the very end, you're going to have this disk thing here. Of course, that's when x is equal to 3. And then you'll have a slightly smaller one after it. And I'm trying to, I hope I don't ruin this with my bad graphing. But, you know, this continues all the way down. I'll be interested in particular, what I'll be interested is in a generic one. And this goes down, down, until we get to close to the very end. Well, you get the idea. So you're going to have a bunch of stacked disks here. Well, what's the volume of each of these disks? Well, let's call this guy X is where it's located at. And let's take a look at how at the volume of that one thing. So pick a generic disk. I don't really care. Center is at X. The volume of that disk. You know, I'm going to put an X sub K here because we do, remember it starts here at X sub 0. That could be like X sub 1, etc. You get the idea. That's the locations of the centers of these disks. So let me see the volume of that disk. That's going to equal, well, here's a perfect example. If you look, it is a shape with a circular base and a uniform height. So in these cases, it is the area of the base times the height. So that equals the area of base times the height. So let's take a look and see what we have here. The area of the base is going to be, well, that's a circle, so the area of the base is pi r squared. And the height, I'll just call h for now. Now let's take a look at those things. Well, one of the things that we do first when we did any of these, if you'll remember correctly, each of these thicknesses, we found that the easiest way to figure out these areas is if we use the same thickness for each and every one of them. So what I'm going to do is call all of them to have a thickness of delta x. Delta x. So no different here. This will be delta x. So that is, in effect, my h. Now the r, what is that going to be? Well, let's take a look here. We can figure out the r. If we go from the base to up here, well, isn't that f of xk? That is f of xk. Well, what is f of xk except this? 1/3 x sub k. So r that's because y equals 1/3 x. That gives you the radius. That's actually the height, if you will, of the disk. So v disk equals pi. My r was 1/3 x sub k squared, and the height was delta x. Well then, the volume of all the disks. The volume contained in all the disks is going to be the sum, where k equals 1 to n. That'll be pi times 1/3 x sub k squared delta x. Now, let n go to infinity to get the exact volume of the solid, they call it a solid, of revolution. So v equals the limit as n goes to infinity, summation k equals 1 to n, pi times 1/3 x sub k squared delta x. And you should recognize this, especially if you're one of my students, you should recognize this as the definite integral of pi times 1/3 x squared dx. Where is the beginning and where is the end of this thing? Well, you can either go by the graph, and we started when x equals 0 and ended when x equals 3. Another way you can do it is if you know that x sub k is the same as just k, then in a situation like that, well, no, it's actually not true. 3 over n times k. But what you could do in those cases is if you let k equal 0, you would get 0 for the lower limit, and let k equal n to get 3 for the upper limit. But however you have to do it, And now let me go ahead and compute this integral. I'll bring the pi out, and this 1/3, if I square it, will be 1/9. So I'm going to have pi over 9. The integral from 0 to 3 x squared dx is going to equal pi over 9 times x cubed over 3. And that'll go from 0 to 3. Then we have, looks like 3 cubed will be 27 pi. So I get 27 pi over 27. Of course, if you plug in x equals 0, that's just 0. And this equals pi, which agrees with what we had said earlier. So now you had a general idea of the overview. All right, so hopefully you understand or you believe the method works. Now we'll do more unusual examples, ones that we don't already know the formula for. So for my second example, I want you to consider the region in the plane bounded by the graphs of y equals e to the negative x, y equals 0, x equals 0, x equals ln 4. So remember, bounded means I have to find a region of finite area that these graphs contain within. So once again, you can graph this on your calculator if you want, but I don't think any of these are really that difficult. Most people know that the graph of y equals e to the negative x comes in when y equals 1 and just decreases. And we have to stop when x gets to ln of 4. Okay. Y equals 0 is the x-axis. So that is a bound. And then x equals 0 is the y-axis. So what they're talking about then, x equals ln 4 technically is the vertical line that goes here. So what we're talking about is this region here. It is literally bounded by those 4 curves. It is inside of this graph because it's under it. It is above y equals 0. It is to the right of x equals 0 and to the left of x equals ln of 4. So here they are. The way that you know the region is, it'll be typically the only one on the graph that is actually contained or bounded, finite area. But let's go and do the same thing as before. Revolve the region about the x-axis. So what are we going to get? I am not sure it matters what the figure looks like and that it's necessary to know it to get the answers to this. So for example, if you look at this part, I'll get like something like this. It'll go to 1, come down to -1. You'll have a region like that. And then here at ln of 4, how tall is it? About that tall. You have something like this. Some kind of a weird horn-shaped thing, something like that, is what you're going to have. And if you really want to, you can make these dashed lines if you want behind it to give it more of the illusion of 3-dimension. But I don't think you have to. Now, what I'm going to do is the same thing as before. I'm going to look at rectangles, cut this region up into rectangles. So we're going to say, what is the volume? What is the volume of that solid? So we're going to proceed like before. And you'll draw rectangles like such. Do you remember the right? I believe they call this the right endpoint method. It doesn't, you don't have to use it. It really doesn't matter what you use. But you get the idea. And once again, to get a formula, we don't have to write for everything. All we've got to do is pick one particular one. And it's better even, instead of xk, it might be better just to do x. So let's pick this as our guy then. And let's say I have it centered at x. Okay, now let's take a look at that. After it's revolved around the x-axis, what are you going to get? So let's take this guy and see what it looks like. It is going to be okay, so you get a disk like this. What do we need is we need to know the radius of the base, and I need to know the height. Well, the height I have, that's delta x. We'll always use delta x for that. Now the radius, that's going from the center to an edge. That'll be the radius. What is r equals what? Well, r is the height of this guy. How tall is that rectangle? Well, for that rectangle right there, that will be f of x. Well, what is f of x? F of x is, in this case, the height curve is y equals e to the negative x. So we get e to the negative x. All right, so the volume of the disk, the volume, I'll call it v sub disk, equals pi r squared h, which equals pi e to the negative x squared delta x. And then this will allow you to get the volume of the whole thing is simple then. I don't have to worry about sums or anything like that. The grandstanding volume then is simply pi times the integral. Now, where is the beginning and end of this thing? The region begins when x equals 0 and ends when x equals ln 4. So this will go from 0 to the natural logarithm of 4. We have e to the negative x squared dx. To make life a little bit easier, this equals pi times the integral from 0 to ln of 4 e to the negative 2x dx. And that equals negative pi over 2 e to the negative 2x. And we're going from 0 to ln of 4. And this equals negative pi over 2 times e to the negative 2 ln 4 minus negative pi over 2 e to the negative 2 times 0. I can do a lot of simplifying here. For this part right here, you might find it easier to rewrite this exponent as ln 4 to the negative 2. For the other part, it's pretty simple. It will become plus just pi over 2 because e to the 0 is 1. The reason I went through this trouble is because the e and the ln cancel each other, and I have negative pi over 2 times 4 to the negative 2 plus pi over 2. 4 to the negative 2 is 1 over 16, so I have negative pi over 32 plus pi over 2. If I change this to 16 pi over 32, you'll see that my final answer is 15 over 32 pi. As a note, you may... No, I don't think that word's good enough. Not strong enough. Doesn't say you may not. Like that. Like it's. I'm telling you, might not. You cannot get a negative answer. You're talking about volumes. Volumes can never be negative. Consider the region in the plane bounded by y equals 1 over the 4th root of 1 minus x squared, y equals 0, x equals negative 1/2, x equals 1/2. I'm going to draw it. This should not surprise you. You can do this with your calculator if you want, but honestly, you don't need that great of a graph. I'll explain to you how I come about my graph. For one thing, it's an even function, so it's going to be the same on the right side as the left side. When x is equal to 0, this is y is equal to 1. So I'll put it up here. And then what's going to happen is x goes to infinity, this will go to 0. So it's going to do something like this. It's probably going to, I don't know how it's going to curve, if it's going to be strangely curved or not, or whatever it's going to do, but it might do something like that. Throw it on your calculator and see. I happen to know that whatever happens on the right happens on the left because it's an even function. So let's see if I can make it. That's a weak effort. Anyways, I am talking about the region in the plane bounded by this curve, y equals 0, which is the x-axis. So far I've got the region between the graph and the x-axis. And then it gives me x equals negative 1/2 and x equals 1/2. So this is the region we're talking about here. Now, I think what I'm going to do is I will take advantage of the symmetry of this even function and really just work half of the graph. And then I'll multiply my final answer by 2. So, by symmetry, I'm just going to work 1/2 of it. So just work 0 less than or equal to x less than or equal to 2, and then multiply by 2 because of symmetry. So let's take a look at that side of things. And as before, I'm not really going to concern myself with a bunch of rectangles. I'm going to concern myself with just one rectangle. And as usual, this rectangle will be at x. All right, so remember, we're going to revolve this around the x-axis. Actually, the question wasn't done yet, was it? Well, we're going to revolve it around the x-axis. So I'll say now all right, so we revolve it around the x-axis. We're going to do like we did before. Let me get the volume of the disk. So take this guy right here and revolve it, and you're going to get something that looks like this. Okay, the thickness is always going to be delta x. And what's the radius? Tell me what r equals. Well, r equals this height. The height is f of x, which is just going to be, what was this? I need to know this curve was 1 over the 4th root of 1 minus x squared. So the volume of a disk equals pi r squared h equals pi, and I'll put r 1 over the 4th root of 1 minus x squared. I'm going to be squaring that. And then h, of course, was delta x. So when I square it, notice that this is going to just become the square root. So this equals pi times 1 over the square root of 1 minus x squared delta x. So then the volume for my answer will equal pi. What are our limits of integration? They're going to go from 0 to 1/2. And then I'm going to have 1 over the square root of 1 minus x squared dx. I'm missing something here. Do you remember I said I had to multiply my final answer by 2? So let me get this out of here. This, of course, the antiderivative of 1 over the square root of 1 minus x squared is arc sine of x. So I'm going to get 2 pi arc sine of 1/2 minus 2 pi arc sine of 0. So I get 2 pi. Arc sine of 1/2 is pi over 6. Arc sine of 0 is 0. So I end up with pi squared over 3. In all the examples we've considered so far, the axis of rotation, the thing that we're revolving around, has always been right up against the graph itself. What happens when the axis of revolution is not next to the region? So, for example, we could have something like this. I could have, I don't know, whatever, a region, let's say like that. And let's say that it's not along the x-axis, but I'm rotating it. Maybe even, let's just say I'm actually rotating it about a line, maybe even. So let's say the region is revolved about the line y equals L. So you can see it's not right up against there either, and we have a weird looking bottom, etc. So we revolve it about this line. What are you going to do? You're going to, if you take a look and you make these rectangles like we did before. Let me go ahead and now, if you take a look at that rectangle and you revolve it about this line, here's what's going to happen. You're going to get the shape of a lifesaver. Maybe that's not the best one. A washer. It's going to look like this. This region in here when you revolve it around, you're going to get something like this. I think the easiest thing for me to do is to draw just the disc shape, but then I'll take out the center. So you have something like this, but then you'll have the middle part taken out. And of course, that's the line y equals L right in the center of this thing. So now, this is a little bit different than before, because now you have what you would call an inner radius and an outer radius. So let's just say, I don't know if I can fit it in here, but that little thing there will be a little r, and this big one will be a big R. So you'll have big R will be outer radius, and then little r will be inner radius. Well, what's the volume of this disk now? Well, the volume of this washer, they call it a washer, which hopefully everybody knows that's the shape of a washer. But the volume of this washer is V equals pi. Now, it's not quite the same as it was before. If this were filled in, it would be pi r squared. But you have to subtract this piece out, which is pi little r squared. So what you're going to end up getting is pi times capital R squared minus little r squared. I made a mistake. Pi r squared minus r squared times h. H is the height, of course, because it would be the same height for both of them when you subtract it out. You'll see. Take a look in the book, or just try it yourself. Subtract the little one from the big one, and this is what you'll get. I want to go back to an example that I did last time. Consider the region in the plane bounded by y equals 10 minus x squared and y equals x squared plus 3x plus 1. Compute the volume of the solid formed by rotating the region about the line y equals 11. So let me just get a quick graph from this thing from last time. Remember, this last one had a height of 10. It's parabola. Both were parabolas. And the region went something like, I think it went a little bit under, something like this. And then like this, I think. And then the lower limit was -3, and the upper limit was 3/2. And this is the region right here. Now we want to revolve that, or rotate that, about the line y equals 11. So this is our axis of revolution. Now, what you got to do, just like before, make yourself a single rectangle. It doesn't matter where, it doesn't matter, but it's at x. That's what's important. And the thickness, of course, is delta x. Okay, Now take a look. If you rotate that about this line, y equal 11, I find that if you make them too circular, they look ridiculous. Even that looks ridiculous to me. But nonetheless, let me put the inner circle in here. And there we are. There's our washer. Okay. Now what we need are two things. We need a smaller radius. That would be little r. And then we need an outer radius. That one right there would be big R. Better yet, let's do it this way. From here to there, this distance here, that's little r. And then from the center all the way down to this graph, so for this particular x, we would have so I need to get my r's, the big R and the little r, and then I'll be able to work this problem. So capital R equals, all right, so it's going to be the distance from a height of 11 down to these y values, which is the graph. What is this graph that bottoms out there? That was the x squared plus 3x plus 1. So you'll have 11 minus x squared plus 3x plus 1. And I'll simplify a little bit of that. We will get 10 minus 3x minus x squared. I have this penchant for wanting to go in some order from lowest to highest or highest to lowest powers. Then the other one, the little r, that was equal to 11. We had 11 minus this, the height of this curve, that was 10 minus x squared. So 11 minus 10 minus x squared. And that equals 1 plus x squared. So the volume of a disk, actually let's call it a washer this time. The volume of a washer equals pi r squared minus little r squared. That equals pi. The capital R squared was 10 minus 3x minus x squared. And then you're going to square that. Minus 1 plus x squared squared. And that equals pi times 99 minus 60x minus 13x squared plus 6x cubed. Obviously, I intend for you to do this painful stuff of multiplying this all out. There's nothing, I have no shortcut for you other than multiplying it all out. And you know what, I keep forgetting about these things. Okay, anyways. Then the volume that we seek, we have the volume equals pi, the integral, and it was going from -3 to 3/2, 99 minus 60x minus 13x squared plus 6x cubed dx. This ends up equaling 12,879 over 32 times pi. one last example, and this is one where you're thrown a little bit for a loop. Consider the region in the plane bounded by y equals 0, y equals 1, y equals ln x. Compute the volume of the solid formed revolving the region about the line x equals -1. Well, let's get a picture of this. I am between y equals 0 and y equals 1. I'll draw y equals 1 way up here. Okay. All right, so I'm between here and here. Y equals ln x. Ln x comes and crosses the x-axis at 1. And now eventually, ln and this do intersect. So where does that happen at? That happens out there at E. So what do we have? Y equals 0. It's in between these two, right? And then, is there any other bound here? We must have another bound. There is one more bound that I did not include. Let me put it up here. X equals 0. So that would be x equals 0 would be the y-axis. Okay, so I'm between here, 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 and here. Hopefully you'll see that that forces the area of the region to be here. So there's my region. Now, we want to rotate this about the line x equals -1. Now this is different immediately than any of the other problems because this thing is vertical. All the other ones were horizontal, the things we rotated around. So how is this going to work now? We're going to have a strange looking anvil type figure when we're done. I don't know that it matters what you do there, but let's see. If we try to do a washer, that means if we try to do something like this. Well, we did that as long as we were going around a horizontal line. We would get a washer shape or a disc shape or something like that. That's not what I want. What are we going to do now? Well, what we can do is this. Let me get rid of that. A couple of these. Give me one more. Good. What we can do then is we can create horizontal washers. The problem with a horizontal washer is that you're now dealing in the realm of y. I'll tell you what I mean. Now your height is going to be at y, and when you rotate it about this line, you're going to get a figure that looks like this. It had a pretty small hole in the middle. You're going to get a figure like this. Well, the height is vertical this time. So instead of delta x, you're going to do delta y. And now your inner and outer radiuses are different. Look at this. From r is literally the little r. The little r is easy. The little r is just from x equals 0 to x equals -1. That distance is 1. No big deal. So I'll have little r equals 1. What about the big R, though? The big R, how can I do it? The big R goes from here to here, so we'll have the big R. Well, what's that going to be? Well, that's going to be this x value minus -1. So the big R, well, this x value, I noticed what I said, the x value. Well, what is this? This here was y equals ln x. But if I wanted to change it to an x value, I can rewrite that as x equals e to the y. Isn't that so? I can change this equation to x equals e to the y. Now I got it in terms of y. That's important since this is the way I'm proceeding. So it's going to be that minus -1. And then if we do the volume of a washer, that's going to be pi capital R squared minus little r squared. That's going to equal pi. Capital R was e to the y plus 1. And little r was 1. This is really simple. This equals pi e to the 2y plus 2e to the y. The 1's will end up canceling out. And that's all you have to integrate. So don't forget its thickness. I don't know why these washers just dumbfound me. So delta y, delta y, delta y. And then the volume will be pi times the integral. Now the integral, the lowest y value is 0, and the highest y value is 1. And we get e to the 2y plus 2e to the y dy. And I'll leave it to you to get pi over 2 e squared plus 4e minus 5. Okay, one last thing. And that is beware of formulas. Students in these classes typically write formulas, lots of formulas down. In fact, I've even let students use formulas on their tests and things like that. And they're fine, but a formula without the understanding of what you're doing in it is not helpful. And not only that, textbooks have a way of giving such a simplified version of the formula that it's nearly impossible to figure out how to take their formula and adapt it to the problem at hand. You'll notice I wrote no formulas here, other than the formulas for the volume of simple three-dimensional objects, like the disks, actually just disks. That's it. So I have nowhere actually written down the general formula that you'll find in a textbook. if you want to go that route, go ahead. Chances are 9 out of 10 of you are going to do exactly that. But maybe that 1 out of 10 of you won't. And you'll see that it's not so bad to actually derive each of these as you come to them. And each one's a separate problem, but the geometry, the basic geometry that you're going to use, and then the integration technique and all that, they're all the same for every single problem. So anyways, I come off my soap opera, my soapbox, and I'll call this one quits.